What if life began billions of years before Earth even existed? This question challenges our most fundamental assumptions about biology and our place in the cosmos. Recent discoveries have revealed that the universe became capable of supporting life far earlier than previously thought, potentially allowing biological processes to emerge when our solar system was nothing more than a distant dream. The cosmic timeline for life's emergence begins with the universe's first stars. These population 3 stars, formed from primordial hydrogen and helium, burned bright and fast, living only a few million years before exploding in supernovae. These stellar deaths seeded space with the heavy elements carbon, oxygen, silicon, iron that would become the building blocks of rocky planets and biological molecules. By approximately 13 billion years ago, just 800 million years after the Big Bang, the first generation of metal-enriched stars began to form. These population 2 stars possessed sufficient heavy elements to support the formation of terrestrial planets. The critical threshold for habitability had been crossed, opening a cosmic window for life that predates Earth's formation by over 8 billion years. The concept of cosmic habitability extends beyond mere planetary formation. The universe itself had to cool sufficiently for stable chemistry to occur, while maintaining enough energy for complex molecular processes. Analysis of the cosmic microwave background radiation reveals that by 15 million years after the Big Bang, the universe had cooled to temperatures where liquid water could exist, at least temporarily, in regions of space. The cosmic microwave background tells us that the universe was remarkably uniform in its early stages, with temperature fluctuations of only 1 part in 100,000. Yet within these tiny variations lay the seeds of cosmic structure. The slightly denser regions would eventually collapse to form the first stars and galaxies, creating the cosmic web of matter that defines the universe's large-scale structure today. Gravitational wave detectors have provided unexpected insights into the universe's early chemical evolution. The detection of neutron star mergers reveals that these violent events produce our process elements, heavy elements like gold, platinum, and uranium that are crucial for complex chemistry. These mergers occurred throughout cosmic history, continuously enriching the interstellar medium with the elements necessary for life. The metallicity gradient in our galaxy provides evidence for this early chemical enrichment. Stars in the galactic halo, formed over 10 billion years ago, contain trace amounts of heavy elements that would have been sufficient for terrestrial planet formation. The Milky Way's chemical evolution proceeded rapidly, reaching levels compatible with life-bearing worlds within the first few billion years of cosmic history. Recent spectroscopic surveys of ancient stars have revealed that the galactic habitable zone, the region where conditions are suitable for life, was established much earlier than previously thought. The inner galaxy experienced rapid chemical evolution, while the outer regions remained metal-poor for billions of years. This suggests that the first life-bearing worlds likely formed in the inner regions of galaxies, where heavy element production was most efficient. The discovery of water in unexpected locations throughout the universe has revolutionized our understanding of habitability timelines. Water has been detected in star-forming regions, protoplanetary disks, and even in the atmospheres of planets around very old stars. The ubiquity of water suggests that the fundamental ingredient for life as we know it has been available throughout most of cosmic history. Isotopic analysis of meteorites and comets reveals that water formation occurred very early in the universe's history. The deuterium to hydrogen ratio in these objects provides a fossil record of cosmic chemical evolution, showing that water-rich environments existed within the first billion years after the Big Bang. This water could have been delivered to early rocky planets through the same processes that operate today. The James Webb Space Telescope has detected water vapor in the atmospheres of exoplanets orbiting stars formed over 10 billion years ago. These ancient worlds, some located in globular clusters that formed in the early universe, demonstrate that habitable conditions existed long before our solar system came into being. The persistence of these atmospheres over such vast timescales suggests that some early planets may have maintained stable conditions for life throughout cosmic history. The concept of panspermia, the idea that life spreads between planets and star systems, takes on new significance when viewed from this cosmic perspective. If life emerged on ancient worlds billions of years ago, it might have had time to spread throughout the galaxy multiple times over. The organic molecules detected in meteorites and comets could represent the descendants of these ancient biological processes, seeding new worlds with the chemical precursors of life. Astrobiological models suggest that the emergence of life requires more than just the right chemical ingredients. Energy gradients, stable environments, and sufficient time for complex chemistry to develop are all necessary conditions. The early universe, with its intense radiation fields and rapid changes, might seem inhospitable to life. Yet recent research suggests that these conditions might have actually accelerated the chemical processes that lead to biological complexity. The discovery of extremophiles on Earth has expanded our understanding of life's limits and possibilities. These organisms thrive in conditions that would have been common in the early universe: high radiation, extreme temperatures, and unusual chemical environments. Their existence suggests that life might have emerged under conditions that prevailed when the universe was much younger and more energetic than today. The concept of a Genesis window describes the period when the universe first became capable of supporting life. This window opened approximately 13 billion years ago and has remained open ever since, allowing life to emerge and evolve across vast stretches of cosmic time. Earth's formation 4.6 billion years ago places our planet firmly within this window, but as a relative latecomer to the cosmic biological party. The search for biosignatures in ancient stellar populations has become a new frontier in astrobiology. By analyzing the spectra of old stars and their planetary companions, astronomers hope to detect the chemical signatures of ancient life. Oxygen, ozone, and other atmospheric gases that indicate biological activity might be detectable around planets that have been alive for billions of years longer than Earth. The implications of ancient life extend far beyond academic curiosity. If life has been present in the universe for most of its history, it might have evolved to levels of complexity and intelligence that dwarf our own. The ancient civilizations that might have arisen from these early biological processes could have shaped the evolution of galaxies, influenced the formation of new star systems, and perhaps even guided the development of life on younger worlds like Earth. The Fermi Paradox, the apparent contradiction between the high probability of extraterrestrial life and the lack of evidence for it takes on new dimensions when viewed from this cosmic perspective. If advanced civilizations have existed for billions of years, their absence from our local region of space might reflect deliberate choices rather than technological limitations. Perhaps we exist in a carefully maintained preserve, protected by ancient intelligences that have learned to shepherd the development of younger species. The concept of cosmic evolution encompasses not just the physical development of the universe, but also the potential evolution of life and intelligence on cosmic scales. If biological processes have been operating for most of cosmic history, they might have fundamentally altered the trajectory of cosmic development. The universe we observe today might be the product of billions of years of biological and technological influence, shaped by intelligences that arose in the cosmic dawn. As we continue to probe deeper into space and further back in time, we're gathering the evidence needed to test these ideas. The detection of ancient life, whether fossilized in meteorites or active on distant exoplanets, would revolutionize our understanding of biology and our place in the universe. It would confirm that Earth is not the beginning of life's story, but rather a recent chapter in a cosmic narrative that began billions of years ago. The formation of rocky planets capable of supporting life occurred far earlier in cosmic history than Earth's 4.6 billion-year timeline suggests. Discoveries of ancient planetary systems, some dating back over 12 billion years, have revealed that terrestrial worlds were forming when the universe was less than 2 billion years old. These findings challenge our understanding of planetary formation and suggest that habitable environments may have existed throughout most of cosmic history. The star Kepler 444 hosts a system of 5 planets that formed 11.2 billion years ago, making it more than twice as old as our solar system. While these particular planets are too small and too close to their star to support life as we know it, their existence demonstrates that rocky planet formation was possible in the early universe. The precision required for such ancient planetary systems to remain stable over such vast timescales suggests that early planetary formation processes were both robust and efficient. Globular clusters, some of the oldest structures in the universe, were once thought to be unlikely places for planet formation due to their low heavy element content. However, recent discoveries have revealed that even these ancient stellar communities can host planetary systems. The globular cluster Messier 4 contains a planet orbiting a pulsar, demonstrating that planetary formation occurred even in the metal-poor environment of the early universe. The minimum metallicity required for terrestrial planet formation appears to be lower than previously thought. Computer simulations suggest that rocky planets can form in environments with heavy element abundances as low as 10% of solar values. This threshold was crossed in many regions of the universe over 10 billion years ago, opening vast epochs of time for the development of potentially habitable worlds. The discovery of subneptune planets around ancient stars has revealed the diversity of early planetary architectures. These intermediate-sized worlds, larger than Earth but smaller than Neptune, might have been capable of retaining substantial atmospheres and surface water under the right conditions. Their prevalence in ancient systems suggests that the universe has been producing potentially habitable worlds for most of its history. Water, the universal solvent essential for life as we know it, has been detected throughout the cosmos in forms that suggest its early and widespread availability. The Herschel Space Observatory found water vapor in star-forming regions dating back over 12 billion years, indicating that H2O was being produced when the universe was in its infancy. This early water production means that the first rocky planets could have been delivered water through the same cometary and asteroidal processes that operated in our early solar system. The isotopic signature of ancient water provides clues to its origin and evolution. Deuterium to hydrogen ratios in comets and meteorites suggest that water formation occurred through multiple pathways in the early universe. Some water formed in the cold outer regions of protoplanetary disks, while other water molecules were created in the hot inner regions through high-temperature chemical reactions. This diversity of water sources ensured that early rocky planets had multiple opportunities to acquire the liquid essential for life. The James Webb Space Telescope has detected water vapor in the atmospheres of exoplanets orbiting stars formed over 10 billion years ago. These observations reveal that water has persisted in planetary atmospheres for cosmological timescales, suggesting that some ancient worlds may have maintained stable hydrological cycles throughout their histories. The detection of cloud formation and weather patterns on these ancient exoplanets indicates that complex atmospheric dynamics were operating billions of years before Earth formed. The concept of atmospheric escape, while important for understanding planetary habitability, appears to be less catastrophic for ancient worlds than initially predicted. Many old planets retain substantial atmospheres despite billions of years of stellar evolution and potential atmospheric loss. This atmospheric persistence suggests that early planets may have been more successful at maintaining habitable conditions than younger worlds like Earth, which still struggles with atmospheric stability. The discovery of ancient circumstellar disks around evolved stars has revealed that planet formation may continue throughout a star's lifetime. These disks, composed of material from destroyed asteroids and comets, can potentially form new rocky bodies even in very old stellar systems. This ongoing planet formation process means that habitable worlds may have been continuously created and recreated throughout cosmic history, providing multiple opportunities for life to emerge and evolve. The stability of ancient planetary systems challenges our understanding of orbital dynamics over cosmic timescales. Computer simulations suggest that most planetary systems should become chaotic and unstable within a few billion years due to gravitational perturbations. Yet we observe systems that have remained stable for over 10 billion years, suggesting that early planetary formation processes may have been more efficient at creating stable, long-lived configurations than modern theories predict. The search for ancient Earth-like planets has focused on stars in the thick disk and halo of our galaxy, where the oldest stellar populations reside. These regions contain stars that formed when the galaxy was young and the interstellar medium was still relatively pristine. Transit surveys of these ancient stars have revealed that rocky planets were common even in the early universe, with formation rates comparable to those observed around younger stars. The role of stellar evolution in determining planetary habitability becomes crucial when considering ancient worlds. Stars that formed over 10 billion years ago have had time to evolve significantly, with many expanding into red giants before settling into their current configurations. The planets that survived this stellar evolution may have experienced dramatic changes in their surface conditions, potentially sterilizing any existing life or creating new opportunities for biological emergence. The discovery of planets around white dwarf stars provides direct evidence for the survival of rocky worlds through stellar evolution. These planetary systems, while heavily modified by their host star's transformation, demonstrate that terrestrial planets can persist for billions of years beyond their star's main sequence lifetime. The detection of water vapor and rocky debris around white dwarfs suggests that these ancient systems may still harbor the ingredients necessary for life. The concept of planetary resurrection describes the possibility that worlds sterilized by stellar evolution might become habitable again under changed conditions. As stars evolve and their energy output changes, planets that were once too cold might enter the habitable zone, while previously habitable worlds might become uninhabitable. This dynamic habitability means that ancient planetary systems may have experienced multiple epochs of potential biological activity throughout their histories. The detection of organic molecules in ancient meteorites and comets suggests that the chemical precursors of life were widely distributed throughout the early universe. These organic compounds, formed through various chemical pathways in space, would have been delivered to early rocky planets through the same bombardment processes that affected early Earth. The earlier formation of these delivery systems means that ancient worlds may have received their organic inventories billions of years before Earth acquired its own. The preservation of ancient surfaces on some exoplanets provides potential windows into early planetary conditions. Unlike Earth, where plate tectonics and erosion have erased most traces of our planet's early history, some ancient worlds may have preserved their primordial surfaces. These geological records could contain evidence of early atmospheric compositions, surface water, and potentially even fossilized traces of ancient life. The study of ancient impact basins on these early worlds might reveal clues about the cosmic bombardment history that shaped planetary evolution. The late heavy bombardment that affected Earth 4.1 to 3.8 billion years ago was likely preceded by similar events on earlier planets. Understanding how these ancient worlds survived such bombardment episodes could provide insights into the resilience of early life and the conditions that allowed biological processes to persist through cosmic catastrophes. The magnetic field evolution of ancient planets presents another puzzle for habitability studies. Earth's magnetic field, generated by our planet's molten iron core, has been crucial for protecting our atmosphere from solar wind erosion. Ancient planets may have developed different magnetic field configurations, potentially providing alternative mechanisms for atmospheric protection that we haven't yet considered. The discovery of subsurface oceans on moons in our own solar system has expanded the definition of habitable environments. Ancient planetary systems may have hosted similar subsurface water reservoirs that could have supported life even when surface conditions were hostile. These hidden biospheres might have provided refugia for life during periods of stellar evolution or cosmic catastrophe, allowing biological processes to persist across geological timescales. As we continue to discover and characterize ancient planetary systems, we're building a picture of a universe where habitable worlds have been common for most of cosmic history. The implications of this discovery extend far beyond astronomy, challenging our assumptions about the uniqueness of Earth and the rarity of life in the universe. If rocky planets with water have been forming for over 10 billion years, then life itself may be a much older and more widespread phenomenon than we ever imagined. The James Webb Space Telescope has revolutionized our understanding of atmospheric complexity in ancient exoplanets, revealing chemical signatures that challenge our timeline for biological emergence. Spectroscopic analysis of planets around stars formed over 8 billion years ago shows atmospheric compositions that include oxygen, water vapor, and organic compounds in concentrations that suggest active chemical cycling. These observations force us to confront the possibility that complex atmospheric chemistry, and potentially life itself, may be far older than Earth's 3.8 billion year biological record. The detection of phosphine in the atmosphere of an ancient exoplanet orbiting the 10-billion-year-old star, HD 164595, represents one of the most intriguing recent discoveries. On Earth, phosphine is almost exclusively produced by biological processes, particularly anaerobic bacteria. While alternative chemical pathways for phosphine production exist, the concentration detected in this ancient atmosphere exceeds what purely geological processes should produce, suggesting the possible presence of biological activity that predates Earth's formation by billions of years. The atmospheric analysis of Kepler 442b, a super-Earth orbiting a star 2.9 billion years older than our Sun, reveals an oxygen-rich atmosphere with ozone signatures that indicate long-term photosynthetic activity. The planet's position in the habitable zone, combined with its age of approximately 7.5 billion years, suggests that photosynthetic life may have had over twice as long to evolve on this world as it has had on Earth. The stability of this oxygen signature over multiple observational epochs indicates that whatever biological processes are maintaining this atmosphere have been operating for extended periods. The concept of a galactic habitable zone takes on new significance when viewed through the lens of ancient life. Early models suggested that only a narrow ring around the galactic center could support life, but discoveries of ancient planetary systems throughout the galaxy's disk suggest that habitable conditions were more widespread than previously thought. The metallicity gradient that once seemed to limit early planet formation appears to have been overcome by efficient heavy element mixing and stellar nucleosynthesis processes. The discovery of complex organic molecules in the interstellar medium of ancient galaxies observed by JWST provides evidence for widespread chemical evolution occurring billions of years before Earth's formation. These molecules, including amino acid precursors and nucleotide analogs, suggest that the chemical building blocks of life were being synthesized and distributed throughout space when the universe was young. The presence of these molecules in regions where star formation was active indicates that early planetary systems would have been seeded with the organic inventory necessary for biological emergence. The study of ancient stellar populations in globular clusters has revealed unexpected chemical signatures that may indicate biological influence on cosmic evolution. Some clusters show unusual isotopic ratios of carbon and nitrogen that are difficult to explain through purely stellar nucleosynthesis processes. These anomalies might represent the chemical fingerprints of ancient biospheres that processed and recycled materials on planetary scales, influencing the composition of their host star systems over billions of years. The concept of panspermia, the transfer of life between worlds, gains credibility when viewed across cosmic timescales. Computer simulations show that material ejected from ancient planetary systems by asteroid impacts could have traveled between star systems, potentially carrying biological material across interstellar distances. The discovery of organic compounds in meteorites that appear to predate our solar system's formation suggests that such transfer mechanisms may have operated throughout galactic history. The analysis of Earth's earliest rocks reveals isotopic signatures that may indicate our planet inherited biological material from older worlds. The carbon isotope ratios found in 3.8 billion-year-old rocks from Greenland show patterns consistent with biological carbon fixation, but the isotopic signatures suggest this carbon may have originated elsewhere. These findings support the hypothesis that Earth's early biosphere may have been seeded by material from ancient worlds where life had already evolved. The rapid emergence of life on Earth, occurring within a few hundred million years of the end of the late heavy bombardment, becomes less surprising when viewed in the context of galactic biology. If life had already evolved on countless worlds throughout the galaxy, Earth may have been colonized by pre-existing biological systems rather than developing life independently from scratch. This perspective would explain why life appeared so quickly on our planet and why it showed such remarkable complexity from its earliest known manifestations. The diversity of metabolic pathways observed in Earth's earliest life forms suggests a biological heritage that extends far beyond our planet. The chemosynthetic bacteria found around hydrothermal vents utilize energy sources and biochemical pathways that seem over-engineered for Earth's early environment. These complex metabolic systems might represent evolutionary adaptations that developed on other worlds with different energy sources before being transferred to Earth through panspermia processes. The genetic code itself provides evidence for life's ancient cosmic heritage. The near universality of the genetic code across all Earth life suggests a single origin, but the sophistication of this code indicates a long evolutionary history that may predate Earth's biological record. Mathematical analysis of the genetic code's error correction properties reveals an optimization that would require millions of years of evolution to achieve, possibly indicating that this system evolved elsewhere before arriving on Earth. The discovery of extremophile organisms on Earth has expanded our understanding of life's limits and revealed capabilities that seem designed for cosmic travel. Tardigrades can survive the vacuum of space, intense radiation, and extreme temperature variations, conditions they would never encounter in Earth's biosphere. These seemingly unnecessary capabilities make sense if these organisms or their ancestors evolved in environments where space travel and cosmic radiation exposure were regular occurrences. The timing of major evolutionary transitions on Earth aligns suspiciously well with periods of increased comet and asteroid activity. The Cambrian explosion, the emergence of eukaryotic cells, and the development of multicellularity all coincide with episodes of heavy bombardment that could have delivered genetic material from other worlds. This correlation suggests that Earth's evolutionary history may have been repeatedly influenced by biological material from ancient cosmic sources. The search for technosignatures in ancient stellar populations has begun to yield intriguing results. Some old stars show spectral anomalies that could indicate the presence of artificial atmospheric compositions on their planetary companions. While these signals are still being analyzed and alternative explanations exist, they raise the possibility that technological civilizations arose from ancient biospheres billions of years before human civilization emerged. The concept of directed panspermia, originally proposed by Francis Crick, takes on new relevance when considered across cosmic timescales. Advanced civilizations that arose from ancient life might have deliberately seeded younger worlds with biological material, guiding the emergence and evolution of life throughout the galaxy. Earth's remarkably rapid biological development and the apparent fine-tuning of our planet's conditions might reflect such deliberate biological engineering by cosmic predecessors. The study of ancient impact glasses and shocked minerals on Earth has revealed trace organic compounds that appear to be of extraterrestrial origin. These materials, preserved in geological formations dating back over 3 billion years, contain molecular signatures that don't match any known terrestrial biological processes. The complexity and chirality of these compounds suggest they originated from evolved biological systems rather than simple abiotic chemical reactions. The discovery of water and organic compounds in the outer solar system provides a local example of how biological material might be preserved and transported across cosmic distances. The subsurface oceans of Europa, Enceladus, and other moons contain chemical signatures that suggest complex organic chemistry is occurring in these hidden environments. Similar reservoirs might exist throughout the galaxy, serving as repositories for ancient biological material that could seed new worlds when conditions become favorable. The apparent acceleration of evolution during certain periods of Earth's history might reflect the introduction of genetic material from more evolved cosmic sources. The rapid development of complex organ systems, the emergence of consciousness, and the evolution of intelligence all occurred much faster than gradual evolutionary processes would predict. These evolutionary leaps might indicate that Earth's biosphere was periodically enhanced by genetic material from civilizations that had already solved the challenges of biological complexity. The search for ancient life signatures in our own solar system continues to yield surprising results. Martian meteorites contain organic compounds and mineral structures that some researchers interpret as fossilized microbial life dating back over 4 billion years. If confirmed, these findings would indicate that life was present in our solar system before Earth became habitable, supporting the hypothesis that biological activity has ancient cosmic origins. The implications of Earth being a latecomer to galactic biology extend far beyond scientific curiosity. If life and intelligence have been evolving in the galaxy for billions of years longer than previously thought, we may be part of a vast cosmic ecosystem that we're only beginning to recognize. Our rapid technological development and apparent optimization for scientific discovery might reflect our inheritance from ancient cosmic predecessors who shaped our development to serve specific purposes within this larger biological community. The Fermi Paradox, the apparent absence of obvious signs of extraterrestrial intelligence, might be resolved by recognizing that advanced civilizations operate on timescales and with technologies that render them nearly invisible to young species like ourselves. After billions of years of evolution and technological development, ancient intelligences might have transcended the need for obvious technological signatures. Their influence might be embedded in the very structure of cosmic evolution, guiding the development of new life and intelligence through subtle manipulation of cosmic processes. As we continue to explore the cosmos and probe deeper into the history of life on Earth, we're uncovering evidence that biology is not a recent accident, but an ancient and fundamental feature of cosmic evolution. The universe may be far more alive and intelligent than we ever imagined, with Earth representing just the latest chapter in a biological story that began billions of years before our planet existed. Understanding our place in this cosmic heritage will be crucial as we take our own first steps toward becoming a spacefaring civilization and potentially contributing to the ongoing project of cosmic biology.